All right, hello everyone. We're going to get started here in a minute. I just want to take 2 minutes to do some housekeeping items. There will be an opportunity for a questions and answer session at the end of our talk. And if you have a question, do feel free to put it in the question box in the control panel. These slides will be available for download in the handout box in the control panel as well. So with that, I'm going to go ahead and get started. So my name is Don Yuzerski. I am a geologist with WSP, currently out of Nashville, Tennessee. I do work for our Regulatory Engineering and Geological Services team, otherwise known as REGS. This is a Houston-based team and is a 13-member organization as part of our underground, our larger underground storage team based there in Houston. If you've listened to these webinars before, you've probably seen other talks by other members of our underground storage team. Our team provides industrial clients geological screenings for well site selection, geological and engineering support for permit applications. We also take on communication with government regulators and key public stakeholders, and also importantly, we provide a confidentiality shield to when communicating with regulators and government, so we can be a shield that keeps some of the commercial aspects that are important to hold as confidential business information, hold that with the client and not have it be publicly available until dictated by law. So with that, now you see my face, I'm going to go ahead and turn off my camera for the duration of the presentation. I'll see you all at the end. So today we're going to talk a little bit about what is carbon capture and sequestration, otherwise abbreviated CCS. I gray out capture and because in my world, we don't deal with the capture, and certainly the process requires capture of CO2, and WSP deals with the capture portion. But as a geologist, I'm interested in carbon sequestration, so we typically shorten that. We're also going to talk about why is everybody talking about CCS. You've probably, if you're on this webinar, you've probably noticed an uptick in news stories and businesses inquiring about CCS. We'll go a little bit into the geology of deep saline storage, including the physics of injected CO2 and the fate of that injected CO2. We'll also have an overview of CCS regulations, including avoiding artificial pathways and tracking CO2 plume and pressure fronts with time. And then we'll speculate a little bit on where CCS is going into the future and end with Q&A. So I won't spend any time in the glossary here, but I've put this together just for those of you who download the slides and use them later. This business is very acronym heavy, so it's useful to have kind of a quick reference guide as to the key terms that you're going to hear over and over again. So we have here a graphic basically explaining what CCS is. It can be broadly defined as kind of a three-step process. The first part up there on the upper part of the image there, we have capture of CO2 emissions from industrial sources or directly from the atmosphere. So you can see there there's a couple of images of factories and whatnot, and then I've modified this image to include a couple of fans over there on the right that I'm calling DAC facility. DAC stands for direct air capture. So that is atmospheric concentration of CO2 is at about 420 parts per million, give or take. So there are new technologies that are actually pulling that low concentration of CO2 directly from the air, and putting and holding it in a concentrated form. And the same technology can be applied where concentrations are much higher on the industrial side, and all of this carbon dioxide that gets pulled either from the point source or from the atmosphere gets put into the new or existing pipeline networks and is then piped to a location where you can see the bend there. Now we're going down at least 800 meters into the subsurface, and that CO2 is compressed into a liquid and then injected into the subsurface for what we call permanent sequestration. So we're removing it from the atmosphere, either from the atmosphere directly through DAC or before it gets in the atmosphere from industrial point sources, sequestering it in the rocks where it's not in the atmosphere, it's not going to contribute to climate change. And where, as geologists, we come in is we ensure that storage is permanent and long lasting. So certainly this, in the simplified 3 steps to what the process of CCS, parts 1 and 2, capture and transport are vital to making the entire system work. WSP has expertise and staff to handle the engineering challenges that come along with capture and transport. However, that's not my specialty. We deal with what do we do with the CO2 once we have it in the pipe, and we're going to store it underground and keep it out of the atmosphere. So as interesting as steps 1 and 2 are, we're going to focus on step 3 today. So this slide speaks to the why. Why are we talking about CCS? And what we have here is a graph of carbon dioxide emissions in billions of tons per year. This is just the anthropogenic or human-caused portion versus time, 2015 to 2100. And there's 5 paths there, and those 5 paths are the different scenarios laid out by the IPCC, the Intergovernmental Panel on Climate Change, the UN body. And this was in their 2021 report that had these different scenarios depending on how aggressive the world gets with trying to remove CO2 from point sources and from the atmosphere. And in 2022, the U.S. Energy Agency estimated that the global contribution by humankind was almost 37 billion metric tons of CO2. So you can see where we are, and certainly none of these paths are defined. We haven't really chosen our path yet. Some of these paths get us to net zero by about 2050 to 2075. And then, of course, we have the let it rip scenario where we do very little mitigation all the way almost close to 2100. And all of us on this call, we may not be around in 2100, but the way I look at it is that my son, who is currently 2 years old, will be 79 years old in 2100, presumably with a family that he cares about of his own. And obviously, the impacts of climate change on the let it rip scenario versus these more action-intensive scenarios is not nothing. If the difference between the path that puts us in compliance with the 2015 Paris agreements to hold temperature rise to less than 2 degrees C, and a scenario where we do little to nothing to mitigate climate change, the difference in those scenarios is an additional 500 million people living below what would be the high tide level in 2100. And that's not a total of 500 million people, that's an additional 500 million people. So just that one piece alone, not speaking about other natural disasters or impacts on the food supply, just that one piece, we're talking about mass migration. So this is a what path we take is very going to determine what living looks like in the year 2100. So that's the why, but why now? And one of those reasons is in the United States, we have something called the 45Q tax credits. And the 45Q tax credits are a section of the IRS code, the Internal Revenue Service code, that allows for tax credits that are transferable, which means they can be sold for every ton of CO2 that is sequestered in the subsurface. So at around 80, at an average, they've been growing significantly from 2018 to 2022. But if we take the U.S. share of global emissions and value it at $85 a ton, that's approximately a $400 billion possible market for just the U.S. share of CO2 emissions. And a large CCS project, we'll get into the specifics of the well, but they plan to sequester about 1 million tons of well annually against that 40 billion ton total of anthropogenic CO2. So for what that means in total number of wells, if I do my math right, we're figuring on tens of thousands of wells across the world, either as standalone sequestration sites or in a few thousand of pipeline serviced hubs. And that may sound like a lot of infrastructure, but this should be familiar to some of you because we already do this with the oil and gas industry. That number of wells, those number of hubs, that number of pipelines are already in service, servicing the oil and gas industry. So certainly within humankind's capability to enact. So let's get to the actual subsurface here. We have a graph here. We've got a CO2 injection well on the right that is injecting into our injection zone there in the light green, sandwiched between two what we're calling confining zones. And this is all below the lowermost USDW, which in US terms is the underground sources of drinking water, which is what US regulations seek to protect when it comes to CO2 injection. So we have there our CO2 injection well on the right, and we have these various colors that are emanating from that well. In the darkest green, we have structurally trapped CO2. So CO2, when it's injected into the subsurface, is actually a buoyant fluid. It is lighter than the salt water that exists in the pores in the subsurface, and it will migrate to the top of the zone where it is confined against different rock types. And if you look at the zoom in there, we can see where we have these sand grains that are these large diameter sand grains, and the CO2, the liquid CO2 is trapped between these sand grains, but it runs into our confining zone, which is made up of a cap rock that has much finer grains. So the pore throats, the space between the actual grains and the cap rock is much smaller, and it does not allow the CO2 to flow through it. And these confining zones are necessary to keep the CO2 in the subsurface where it won't impact the underground sources of drinking water, and it won't re-enter the atmosphere, both to prevent warming and also to ensure that those tax credits that the government is allowing companies to claim are properly being accounted for. Now, over time, the CO2, as it mixes with the formation brine, so the salt water that's actually in the rocks, it actually becomes denser than the brine itself, and it begins to fully occupy the entire reservoir in where it eventually is dissolved into the brine and then actually it goes into a mineral or solid state on a multi-thousand-year time scale. So ultimately, we take the CO2 from the atmosphere as a gas and we turn it at long time scales into a solid in the reservoir. So where does WSP and the industry come in to ensure that these sites are sited properly? Well, first the geology has to work. We have to find an injection zone of proper thickness, proper porosity, and it can accept large volumes of CO2, and we have confining zones both above and below that are going to keep the CO2 contained. All right, there are a lot of there's a lot of geology in the world that fits those descriptions, but one of the primary concerns of the regulation and where our REGS team comes in is reviewing and making sure that there's going to be no breach of containment. And one of the key ways that containment through the confining zone could be accomplished and allow CO2 to migrate up into the shallower zones is through what we call artificial penetrations. Now, it's in the literature, or I'm sorry, in the regulations, they're called artificial penetrations, but what we mostly mean are human drilled wells. And there are three types of wells when it comes to siting these projects that we have to tally and be concerned with. The first one there, we have a well. It has a well bore represented by the black line, and it approaches our confining zone, but it does not pass it. So in this case, we do not breach the confining zone, and it does not present an immediate potential pathway for CO2 to contaminate the surface. So we would note it, but we're not concerned with it as a body that wants to satisfy the regulations. The second well there, we have what we call a non-deficient AP. So the wellbore penetrates the confining zone into the injection zone, but there are cement plugs that are isolating the USDW from the surrounding formation, And also there are cement plugs above the confining zone that's going to keep the CO2 trapped within the injection zone. So certainly any penetration that goes through the confining zone, as geologists and engineers, we're concerned with to make sure that the well was properly abandoned. But as long as it was abandoned properly, we're not concerned that the well will be a potential pathway. It only has to be monitored for potential migration in the future. Finally, we have what we call a deficient AP. So this is a well that penetrates the confining zone into the injection zone, but is not plugged in a manner either with the placement of the plugs or the materials that those plugs and casings are made of that allows the CO2 to potentially migrate up to shallower zones. And so before a permit could be issued, these wells need to be addressed, and by potentially re-entering the well and abandoning them correctly. And this is called, in the terms of the regulators of the United States, corrective action. And we're dealing with this at a number of sites. We identify them. We let the operator know that they have some deficient wellbores here, and if they want to proceed with the project, they need to be remediated. And the cost to do that can be significant. It could be in the millions of dollars. It just depends on the specific situation and how deficient the wellbore is. So it's not a trivial issue. So going into the future, once we have a project sited and we've accounted for the wells, the CCS regulations in the United States require an ongoing commitment from the permittee. So the regulations require monitoring of atmosphere, surface, and subsurface to protect the health and safety of both the people living on the surface and the environment. And this is done through tracking of the CO2 plume and the pressure front it creates in the subsurface. And that is done through the drilling of monitoring wells that monitor the concentration of CO2 in the subsurface spatially and temporally, and also through a regular collection of geophysical data, seismic surveys that can be information about the plume and pressure front can be derived from the changes in seismic survey response over time. And we're going to reevaluate those APs at fixed intervals every, say, several years, 5 years into the future, unless our monitoring data shows that there's some deviation from what we're expecting. And the image on the right is of the Decatur project in the U.S. state of Illinois. And this was one of the first CO2 injection wells in the country. It actually predates the regulations. What's called Class 6 in the United States. Class 6 wells are CO2 injection wells, and we see a couple outlines there. We have a yellow outline, and that's the saturation plume that's expected by 2070. So as injection continues, CO2 continues to move in the subsurface because it's buoyant at short-term timescales. And the geologists here on this project, this is not a WSP project, but it is well known and well published about. And the geologists on that project expect the CO2 footprint to have that shape in the year 2070. And then if we look at the purple outline, that is the pressure front created by that CO2 plume on a much shorter time scale. It goes out in front of the plume, and that's where it's expected to be in the year 2020. This injection began at this project in 2017. Those two things taken together form what we call an area of review, and that area of review is constantly monitored by the operator of the CCS well with the help of a WSP that's going to be reviewing their geologic information. And additionally, it's important to note that unlike some of the extractive industries very early on in their histories, decades ago, in this case, the financial strength of the operator is taken into account before a CCS permit is approved, and that a financial instrument, a bond, essentially needs to be posted to ensure that the funds are available to properly close the site after injection ceases, so that the general public will not be stuck with the task of cleaning up orphan wells. In the United States, the permitting body that permits these wells is the Environmental Protection Agency, or the EPA. The regulations are such and the activity are such that the current review time is about 2 years. So these are not these are not short-term evaluations. The permitting process is robust, and again, that's done to ensure public health and safety. And you can see here, this is very new information. The EPA is getting bombarded with permit applications for CCS wells, again, due to the fact that CCS is now commercially viable thanks to those 45Q tax credits in the United States. So the number of permits are increasing drastically, and you can see here that that's just resulting in a review timeline for the regulators to being 2+ years. So as other countries begin developing and clarifying their regulatory standards, it's certainly something to take into consideration if you operate internationally. The regulatory environment may not be a negligible aspect of your project. Finally, WSP takes its role in crafting these permits and evaluating sites for CCS very seriously, and we keep in the forefront of our mind, sustainable development goals. They're listed by the UN, and the process of carbon sequestration, we think, directly upholds at least 12 of those 17 goals. You can see here, protection of the environment, climate mitigation, obviously, sustainable cities and communities, again, protecting drinking water sources. So this is an industrial activity that is not without possible external effects. So the role of a WSP and the role of regulators is to work with the operators and make sure that we're upholding these goals that we have for wider society. And in the United States, this is enforced through executive orders that I have listed at the bottom there. So for those of you with the slides, you can click on there and read about how environmental justice in the United States is very much a part of these permit applications, and that's where WSP can help an operator craft a permit that has the greatest chance of being accepted. So we're reaching the end of our time here, but this was a North American focused talk, because that's mostly where I work in the world. However, there's nothing special about the geology of North America when in regards to carbon sequestration. We're looking here at a map of sedimentary thickness around the world. And although there are large sedimentary basins in North America that we're exploiting for CCS opportunities, again, that's not specific to North America. There are opportunities around the world for CCS. Obviously, it's already been ongoing in Europe and some other spots in the world, but with greater regulatory clarity in other portions of the world, and implementation of incentives like the 45Q or some similar incentives in other countries, we can really start to bend the curve of global CO2 emissions down into the net zero territory. So with that, I just want to wrap up. We have some key takeaways here. The number of CCS projects around the world are rapidly increasing, but the paradigm shift in the United States, although it's happened, it's in its relative infancy. We're only a few years out from the implementation of the commercial incentives to sequester CO2. The deep well sequestration on which the CCS projects rely it's old technology. It's been done by the oil and gas industry for many decades. The geology is familiar. What is new and innovative here is that we're applying it to climate mitigation, and that's all due to the commercial incentives. CO2 injection is not without possible negative effects. We haven't gone into those here, but U.S. regulations are very robust to ensure safety and reliability through the permitting process. What WSP's REGS team is here to help navigate those regulations both in the United States, and we look to grow both domestically and internationally as our clients start to look at projects around the globe. And I know some of you coming into this webinar may be really unfamiliar with a well site and are wondering about, well, what is the footprint that these CCS operations take up. And from the perspective of the sequestration well, you're looking at one. This is not a WSP project, but we're back in Decatur, the Decatur project in Illinois, in the United States, and we're looking at a well that's sequestered over 1 million tons of CO2. So you can see that the footprint is not especially large, and I know that's kind of a hurdle for some people to get over in their minds when they're thinking about, well, how much space do I need to actually do these projects? So with that, I'd like to open the floor for questions. I believe we have some in the chat.
Yes. Thank you, Don, for a fantastic presentation. We have just a few minutes for some questions. You can continue to log your questions in the question box on the GoToWebinar control panel. And also you can download the PDF of this presentation in the handout box on the GoToWebinar control panel. I will start with the first question. How does WSP as a non-operator help operators to become viable? And also, how do we see our role evolve in the future?
Yeah, so WSP is not an operator. We don't obviously own the compression equipment or the well itself. We are regulations. I find it particularly satisfying when a company that has no subsurface expertise whatsoever, let's just say they're a waste management company and they have landfills, for example. Those landfills, as our garbage decomposes, releases CO2, and it currently goes in the atmosphere. And we can help that company say, hey, let's evaluate the geology on your site, and let's get that CO2, rather than letting it vent in the air as a waste product, let's get it into the subsurface and monetize it and actually have you get paid for capturing that CO2. So I see us going into the future expanding to companies that don't know anything about their geology, more than 6 inches below the surface. Help them understand that they have a resource that they can monetize. And furthermore, we're working on a bunch of these permits right now, and we have a number that we've submitted, a number that are in review, and some that are being worked on right now for submission soon. That's only part of the process where I think WSP and our REGS team comes in. Right now, there's a rush to get permits submitted and get on that 2-year approval timeline. But into the future, monitoring the site, making sure that the CO2 plume that's being injected is behaving in a manner that's expected, behaving in a manner that is safe, is going to require a lot of collection of geological data. And a lot of companies are not set up to digest that data and make decisions on it. And that's where WSP comes in, and we can help companies 5, 10, 20, 50 years into the future understand their monitoring data and keep them in compliance with the law.
Thank you. There's a question here. What are the long-term maintenance requirements to ensure the captured carbon doesn't escape, for example, deterioration of the concrete plug?
Right. So a lot of wells, so existing wells, during as we put the permit together for an operator, we have engineers that review well records and look at the cement and the casing that the well was drilled and completed with and built with, and we ensure that they are compatible with a CO2 plume and they won't degrade under that acidic environment, and allow a potential pathway to be created. And if the materials that were used to construct the well are CO2 compliant, then we check that box. If they're not, then that well is potentially a deficient artificial penetration and would require corrective action. So I leave that to an engineer to say exactly how and what corrective action a well that was built with materials that were not compatible with CO2, what that corrective action would be, up to and including just that not being a viable site for carbon sequestration. If there are a number of those wells and either it's too costly or technically impossible to remediate that well, then that's something that WSP and the REGS team would identify early on in the process and tell the operator, this is not a suitable site for carbon sequestration, and not all sites, are suitable. And that's one service we provide on the front end, is rather than jumping in we want to understand the geology and understand the existing wells, and make sure that we're not going to run into an issue with the operator a year down the line into permit submittal. So sometimes the answer is just no, this isn't a good site.
Thank you. We're a bit over time. I will take the last question. We have many more questions coming through. Apologies, we don't have time to cover those, and Don will cover these by email later on next week. So the last question is, how many tons have been sequestered in the UK, in the US to date, and is it also happening in the UK, if you know? Thank you.
So an exact tonnage amount I do not have. There are 3 sites that have been permitted in the United States. One in Illinois, the Decatur project, and then 2 in the U.S. state of North Dakota, which have been permit approved, but are still in the pre-injection phase. So the short answer is very little, probably a slightly more than 1 million tons total. But don't let that small number concern you. The number of projects in the pipe, I showed that one image with the number of permits in the pipe that are currently being reviewed at EPA. A number of these sites are a large site sequesters upwards of 5 million tons between a few wells, and a number of those mega sites are being planned. So globally, we're capturing a little less than 1% of total human emissions, but that's right now. And I expect that number is going to jump significantly into the double digits here within the next 10 years. CCS is not the silver bullet to help mitigate climate challenges in the future, but it's certainly a significant portion of the answer to that problem. So it's quite small right now. I do expect it to grow, and you've seen again the permits that are in the queue just in the United States. So we're gonna get those numbers up pretty quick. As far as what's being done in the UK, I can't speak to specifically what's being done in the UK, but I know there are some mega sites in the North Sea, in Northern Europe. I believe the Scandinavian countries are leading that effort. So CO2 injection, I don't know what their incentive scheme is necessarily in those countries right now, as I believe a number of them are government led, but certainly CCS is ongoing in Northern Europe, and in excess of what's going on in the United States. Although it's a bit of a friendly rivalry, I would hope that who the leader in that sector is goes back and forth.
Thank you, Don, for a fantastic presentation, and thank you everyone for joining us today. We hope to see you in our upcoming sessions, and please feel free to follow up with Don via the contact details shown on the screen.
I'll be happy to have a discussion with whoever wants questions answered.
Thank you. Thanks so much, everyone. I will wrap up the session. Have a wonderful day.
Thank you.